So continuing in our study of homogeneous linear equations with constant coefficients, we've looked at first order equations, we've looked at second order equations, and we saw there how we could have different cases depending on the roots of the auxiliary equation. We looked at the two distinct real roots, one repeated real root, and two complex conjugate roots. And in this video, we will generalize to higher order equations, okay? Of course, we're still in the domain of homogeneous equations, linear equations with constant coefficients. So consider the nth order homogeneous linear differential equation with constant coefficients that you see here. All of the coefficients are constant and an does not equal 0. We follow the same method of guessing a solution of this form, and now we end up with a polynomial of degree n, okay, for our variable m, okay? And so what's the challenge here in comparison to the second order case? It's just solving this higher order polynomial, okay? We don't get nice formulas that we do for quadratic, or even you could get some formulas for cubic and quartic, but then when you get to quintic, there's no general formula that you could get. Even beyond quadratic, the formulas are a bit messy. And so what we're going to do is just kind of review some ideas about polynomials, okay? Because our auxiliary equation there is a polynomial of n degree. So first thing up for review is this linear factorization theorem. If f of x is a polynomial function of degree n greater than or equal to 1, and these m's are, you have k of them, are distinct zeros or roots of f of x, okay? And each of these m's has a multiplicity, of r sub whatever subscript corresponding. So m2 has a multiplicity of r2, mk has a multiplicity of rk, respectively. Then f of x may be written this way, okay? So here you'll have k linear terms raised to the multiplicity of each of these linear factors, okay? And a linear factor, of course, you'll recall a linear factor is of the form x minus a. Okay? And very crucially here, n, the degree of our polynomial, is equal to the sums of the multiplicities. Okay? So if each of these linear factors had a multiplicity of 1, then we'll get n distinct linear factors. Okay? But the issue here is that you get repeated roots, and so you get higher multiplicities than 1. But at the end of the day, the sum of the multiplicities will equal n. Something also important here is the complex conjugate root theorem. If f of x is a polynomial with real number coefficients, okay, which is what we're dealing with our auxiliary equation, we're always going to have real number coefficients, and alpha I beta is a 0 or root of f of x. Okay, 0 and root are the same. Sometimes some people will use 0, other times they'll use a root. Here I'm kind of mixing and using one or the other. Then its complex conjugate, alpha minus I beta, is also a 0 of f of x. And the complex conjugate is just the operation where you take I, to minus I. Okay, that's just complex conjugation. Okay, so if this is a root, then so is this. Given that our polynomial, it has real number coefficients, which is true for our auxiliary equation. So we know that, from the above theorems, our auxiliary equation has n roots, okay, counting multiplicities, of course. And so now let's look at cases depending on the root. One is that we get a real root with a multiplicity Ri. And so we want to know what that root will contribute to the general solution. Okay, we're going to need, for our nth order homogeneous linear differential equation, we're going to need n linearly independent solutions to get our fundamental set. And so with mi having a multiplicity Ri, it's going to contribute to the general solution terms of the form e to the mix, x e to the mix, x squared, all the way to the multiplicity minus 1. So what does that mean? That means if the multiplicity was 1, okay, then all you'll contribute is this. If the multiplicity is 2, then you'll contribute this and this to the general solution. Just as we did in the case of repeated real root for second order differential equations, okay? With the repeated root, we needed these two, and now we just have to generalize because you could have a multiplicity of greater than 2. And so you just keep, increasing the order of the polynomial there, the factor, till you get to Ri minus 1, okay? This here is an I, not a 1. You could kind of see that that's I there. And what about with complex roots? Well, if this is a root, then its complex conjugate is also a root by the complex conjugate root theorem. And in fact, both of these will have to have the same multiplicity. So, this complex conjugate has multiplicity Ri bar. This has multiplicity Ri. Okay. And now, what do these contribute? Okay. And we always look at them in pairs. Well, you do get the same relation where you get the exponential with the alpha I beta x. But what you could do, just as we've done with the quadratic auxiliary equation, is you could add and subtract constant multiples in order to get a linearly independent set that's just real. And so you would end up getting this relation. Okay, so for one complex root and its conjugate both, okay, looking at these together, you would get, say if they had multiplicity 1, you would just get these two, okay? But if it has multiplicity 2, because now we can have a higher multiplicity, okay? We can. So if you had alpha I plus I beta squared, you're going to have to get alpha I minus I beta squared as well. So both of those together, their multiplicities together is 4. And so this would have to be a fourth order polynomial, which we didn't really look at that case when we were dealing with quadratic, of course, because there you can only get 2 complex roots. So now, because we could get repeated complex roots, we also have the same trick. We would just use the reduction of order method to get a linearly independent solution, and you could just multiply by x there, and so you get this pair if your multiplicity is greater than 1 or equal to 2, say, and then you just increase up to Ri minus 1 in much the same way that you do with the real root, except now you're getting pairs, and these pairs correspond to summing and subtracting the exponentials corresponding to this root and its complex conjugate. Okay, so note here that up here we get Ri, because this one has, you could think about it as x to the 0, and so when you go to Ri minus 1, you're really getting Ri. So you're getting Ri, linearly independent solutions, which is of course the multiplicity of mi. And here you're getting 2 Ri, linearly independent solutions, which is the multiplicity of this root plus the multiplicity of the complex conjugate. Okay, so that's why there's that 2 there, is because you're looking at these in conjugate pairs. So just, we're solving polynomials of higher order. And so one rule that's kind of helpful here is Descartes' rule of sign. Suppose f of x is expression for a polynomial function written with descending powers of x. What does that mean? They're written like this, okay? If p denotes the number of variations of sign in f of x, then the number of positive real zeros, counting multiplicities, is one of the numbers p minus 2, p minus 2k, dot, 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 all the way down to either 1 or 0, right? So you always have to subtract by 2, by even number, okay? So 2 times something, so by even number. So what you do is, what is a variation? You look at the sign. So say this one is a positive coefficient, this is a positive coefficient, that's not a variation. But if the next one was negative, then you get one variation, okay? If this was positive and this is negative, then that's one variation. You keep counting all the way down. If this is negative and then this is positive, that's one variation. If they're both negative, you don't get a variation. And so you got to keep going down through and counting the number of variations. That's what we mean by variations. If n denotes the number of variations of sign of f to the f minus x, okay, so you plug in instead of x, negative x, then the number of negative real zeros counting multiplicities, okay, so you do have to count multiplicities. So if one of the roots has a multiplicity of 2, it counts as 2. Is one of the numbers n minus 2, and again you subtract by the even number. Okay, so you count the variations now of f to the minus x. Where is that useful? That could kind of give you a hint about how many real roots you have, how many complex roots you have, especially when you consider the complex conjugate theorem above. So this just helps you sort of figure out the type of roots that you have. It can be useful. We also have the polynomial division theorem. Now, suppose d of x and p of x are non-zero polynomials where the degree of p is greater than or equal to the degree of d. Okay? There exist two unique polynomials, q of x and r of x, such that p of x may be written this way, where either r of x is 0 or the degree of r is strictly less than the degree of d. Okay? We may also write this as p of x over d of x is equal to q of x plus r of x over d of x. Okay, the polynomial p is called the dividend, d is called the divisor, q is the quotient, r is the remainder. If r of x equals 0, then d is called a factor of p. Okay? And so why is that useful? Well, it's, again, part of the trick of solving polynomials of higher order is to divide by linear factors, okay, that correspond to roots of that polynomial. And we'll see a simple example of that. Okay, so just it's important to have this theorem in mind. We also have the remainder theorem. Suppose p is a polynomial of degree of at least 1, and c is a number when p of x is divided by x minus c, then the remainder is p of c. Okay, that's just helpful for, so basically we'll get the factor theorem as a corollary of this. Suppose p is a polynomial, the number c is a 0 of p or a root of p if and only if x minus c is a factor of p of x, okay? So we could see these three theorems at work here in this next example. So we have our third order homogeneous differential equation, linear differential equation with constant coefficients. So check mark all of those, right? We always have to make sure we are in the proper domain. The auxiliary equation is, as you see here, okay, so the 1 here corresponds to the m cubed term because that's the third derivative squared. second derivative corresponds to what's in front of m squared. Now, do we see a y prime term? No. So, you could sort of implicitly say that there's a plus 0m there, okay, if you want to just kind of do this algorithmically. But anyway, so we have this polynomial and we want to solve it, okay? It's cubic. So one thing right off the bat is to see if there's an obvious 0, okay? Here you have this 1 there and a 3. Then you could take a guess that actually m equals 1 is a 0 or root of this auxiliary equation. Okay, and it is. You just plug in 1 and you see that that is a root. So we know by the factor theorem that m minus 1 is a factor. Okay, it gives you a remainder of 0 when you divide by m minus 1. If you divide this by m minus 1, you get a remainder of 0. And let's actually divide this to get the quotient. Okay, so we're going to divide this polynomial, the auxiliary equation, by m minus 1. Okay, and how do we do that? Well, we could do this by polynomial long division or synthetic division. I do both just to kind of give a refresher. So the first thing you got to do is ask how many times does m, what we're dividing by, go into m cubed? And it goes in there m squared times. So, okay, there you'll get the m squared term first. And then you take m squared and multiply it by m to the m minus 1. And when you take m squared and multiply it by m minus 1, you get this term here, m cubed minus m squared. You subtract this, okay, by what you get from that multiplication, and you end up with this term here. And then you ask, well, how many times does m go into this right here, 4m squared? And so you see that it goes in there 4m times, okay? And then you take 4m, multiply it by m minus 1, you get this guy here, 4m squared minus 4m. Again, subtract, you're left with 4m minus 4. How many times does it go into m minus 1? It goes in 4 times, okay? And you multiply 4 by m minus 1 and you get this term here. You subtract and we get a remainder of 0 as we expect, okay, because it's a root and we have the factor theorem. Synthetic division is much quicker, okay? So we want to divide by m minus 1. What we do is take from the linear factor just this, the 1, and we put that there, okay? Be careful, because if this was m plus 1, you would have negative 1 there if it was m plus 1. So, careful with that. It assumes the form m minus c, okay? Where c is positive. So here we just have the 1. And what you do is you write down the coefficients of your polynomial that you're dividing. Here it's 1, 3, 0. So we do have to pay attention here with synthetic division. 0 and minus 4. Take down the 1. Multiply 1 by 1. You get 1. Add 3 and 1 is 4. Multiply 1 and 4. You get 4. Add, you get 4. Multiply 4 and 1. You get 4. Add, and you get 0. Okay, synthetic division is not magic. It's just streamlining the long division, okay? It's giving a quick algorithm for the long division. Definitely you should not do synthetic division if you don't understand long division, okay? But anyway, so we've divided this polynomial by our auxiliary equation by one of its roots, m minus 1, and we're left with this. And now why do we do that? Well, now we factored out the m minus 1. That's what you're basically doing. You're factoring out the m minus 1. And you're now left with a quadratic. Quadratic we could deal with that, right? You could either factor it with the standard factor methods. You could even apply what we just did there and factor out another linear factor. Or you could use the quadratic equation. Once we get down to quadratic, degree 2 polynomials, then we're in familiar territory there. So m1 equal to 1 has a multiplicity of 1. We get a second root, negative 2, but that has multiplicity 2. How does our general form look? Well, this one corresponds to our first root with multiplicity 1. For the one with multiplicity 2, we got to, multiply by x. This should be an x over here. Okay? For the one with multiplicity 2. And that's basically how we solve that problem. All right, so let's look at another example. Here we have this fourth order homogeneous linear differential equation with constant coefficients. Our auxiliary equation looks like this. Now, if instead of a 4 you had a 2 there, and instead of a 2 you had a 1, so if you took these and divided by 2, you just get a quadratic, really. And so it's straightforward to see that you could have factored this auxiliary equation into what you see here. Okay? Now, m squared plus 1 doesn't have any real solutions, but it can be further factored into complex solutions that you see there. So we have m1 is equal to I with multiplicity 2, and m2 is equal to negative I with multiplicity 2. Of course, no surprise because of the complex conjugate theorem. Here our alpha is equal to 0 and our beta is equal to 1. Well, what solutions do we have? From the multiplicity, from the first multiplicity, we get this pair together from this pair. And we need 4 linearly independent solutions to get the general solution of a fourth order differential equation. And so we just take these and multiply by x, okay, to deal with that repeated root, the multiplicity 2. And so our general solution is what you see here. Another sort of helpful theorem there to add to the bag of tricks for dealing with polynomials is the rational root theorem. Suppose f of x is the polynomial that you see there of degree n, with n greater than or equal to 1. And all of the coefficients are integers, okay? So here all the coefficients have to be integers, which is not always a guarantee for differential equations. I mean, it's fair game to have rational coefficients, but suppose they were integers. And if r is a rational root of f, that's crucial. If r is a rational root of f, it's not saying that you need to have a rational root or that you can't have complex or irrational roots, but if r is a rational root, then r is of the form p over q, where the integer p is a factor of the constant term, a naught, and the integer q is a factor of the leading coefficient, an. Okay? So it just helps narrow down the possibilities for rational roots. Again, this does not help us at all for irrational or complex roots. Okay? Just rationals. And don't forget that the integers are a subset of the rationals. So let's see this in practice here. So we have this differential equation. Again, is it linear? Yes. Does it have constant coefficients? Absolutely. Is it homogeneous? Yes. Okay, so we're in the domain of the problems that we're trying to solve here in this section. And so we get our auxiliary equation there. Okay. It's a cubic. And, it's not obvious what, it would be nice to, sort of figure a linear factor and divide, but it's not really obvious what would solve this. So we're going to use the rational root theorem. P is going to be a factor of the constant term A naught. What is A naught? A naught is negative 4. What are the factors, okay, of negative 4? Plus or minus 1, right? You would just take 1 and multiply it by 4, and that's so 1 or negative 1 is a factor. Plus or minus 2 is a factor, 2 times 2, right? Or negative 2 times 2, and so on. And plus or minus 4 is a factor. Okay, those factors correspond to 4 and 1, right? And where we would need to make sure one or the other is negative to get, negative 4. But, when you're considering the rational roots, you just write plus or minus. You don't consider which one is which. You just write plus or minus for each of these. Q is a factor of the leading coefficient an. The leading coefficient here is 3. Okay, it's just the coefficient of the highest term. That's 3, and we get the plus or minus 1 and plus or minus 3. And now, let's look at all combinations of P divided by Q. So here we have plus or minus 1. That's coming from plus or minus 1 divided by plus or minus 1. And plus or minus 2 divided by plus or minus 1 is that. Plus or minus 4 divided by plus or minus 1 is that. And then we go right down the line again. Plus or minus 1 divided by plus or minus 3 is this. Plus or minus 2 divided by plus or minus 3 is this. And plus or minus 4 divided by plus or minus 3 is this. Okay, and so you just try all of these combinations, and it's rather tedious and annoying, but you try them, and you try the positive and negative of each of them, and after trying all of that, we realize that m. And by the way, so if you run through all of these and you don't actually get a root, what does that mean? Does that mean there is a problem with the theorem? No. It just means the root is irrational or complex. Okay? And so we try exhaustively after going through this list, and we get that m1 over 1/3 is a root. What do we do now? Well, we divide using long division or synthetic division by m minus 1/3 linear factor, and we find this quotient once we divide. Okay? And now this is a quadratic. We apply the quadratic formula to that, and we get this over here. These two roots, complex roots. And this is third order, and we found 3 roots. 2 of them were complex conjugates. The other one was a real one. And we end up with this general form here. This corresponds to the real root, and these 2 correspond to the conjugate complex roots. And just as a quick mention there, another trick in solving polynomials is the irrational conjugate theorem. Suppose f of x is a polynomial function with rational coefficients where a and b are rational numbers, such that a square root of b is irrational. Okay? If a plus square root of b is a root of f, then a minus square root of b. So it's important that square root of b be irrational there. Okay? So a and b have to be rational, and square root of b has to be irrational for this to work.